our planet's existence, days were a mere 10 hours long. However, after Theia impacted Proto-Earth to form our moon, the length of a day was rapidly shortened due to the transferred rotational energy from the collision, reducing to only 5 hours in length. By the time the first oceans appeared, days were 6 hours 59 minutes, and by the time the first very primitive lifeforms evolved, days were 10 hours 11 minutes. By 3 billion years ago days were 14 hours 39 minutes, but then this trend suddenly changed 2 billion years ago, by which time days were 19 hours 18 minutes long. All of a sudden, due to the fluctuations and evolution of our planet's atmosphere, the length of days would slowly decrease, with this pattern continuing until 1.094 billion years ago, by which time days were only 18 hours 54 minutes long. The length of a day has subsequently increased ever since, being 20 hours 14 minutes long when the first true animal emerged, a sponge, and 21 hours 33 minutes when the first jellyfish emerged. The first reptile evolved when days were 22 hours 40 minutes long, while the age of the dinosaurs saw days vary between 23 hours 2 minutes and 23 hours 43 minutes long. At the present, every century sees the length of a day increase by 1.78 milliseconds, translating to the additional of a second 56,180 years from now, when days would become 24 hours, 0 minutes, and 1 second long. The vast majority of this ever-lengthening day was caused by tidal friction from our planet's moon, which in turn heavily affected tides whose motions as a whole slowed down Earth's rotation. There are also more instantaneous or short-term asteroid impact factors that can affect the length of our planet's day. For example, depending on the angle and direction that a major asteroid or comet strikes the planet, it can either shorten or lengthen the day by adding or removing rotational energy. However, this change only measures in the milliseconds in the largest of impacts during the last 1 billion years, with an 8.4 millisecond change during the impact event which wiped out the non-avian dinosaurs 66.034 million years ago. The largest of earthquakes, specifically major earthquakes, megathrust earthquakes over magnitude 7.5, can also reduce the length of a day, but by a factor more than 1,000 times smaller than the Chicxulub impactor. The reason for this is best shown via an analogy of a dancer on ice skates. When they spin at a set speed with their arms close to their body straight down, they rotate at a high slower than they would if they stuck their arms straight outwards. This is exactly what occurs during a megathrust earthquake, as a several hundred-kilometer long section of a slab is offset by up to tens of meters, redistributing a portion of Earth's mass ever so closer to the core of our planet. For example, the destructive 2011 Japan megathrust earthquake reduced the length of a day by 1.8 millionths of a second, while the 2004 Sumatra earthquake caused a reduction of 2.68 millionths of a second. The distribution of glacial ice on the planet also can play a factor. Ice age and glaciers, as during the last glacial maximum 20,000 years ago 52 million cubic kilometers more of glacial ice existed than it does today. Glacier formation was favored near the poles, and their presence reduced global sea levels, causing Earth's rotation to slightly speed up. The opposite is now occurring as glaciers melt and sea levels rise, although this is not surpassing the opposite impacts from tidal friction. The length of a day decreases when continental landmasses through continental drift are concentrated near the poles, while it increases when concentrated near the equator. As a final note, I would like to thank my patron Catherine Howell for upgrading their Patreon membership tier to this